So starting off, you said you weren't part of all of the discussion, and as you finished off, actually everyone should be part of the discussion. This project is meant to put up some items for discussion that will be further continued. And the best outcome we could wish for us is actually that people continue discussions on the subjects that we raise here.
No, the best outcome is to implement stuff.
Further down the line. For me, that's what I can expect. So to just let you know what this is about, we're here at the last workshop of the RTLabOS project. And this was a project conceived for helping PowerLab Decay, not only SysLab, but also other labs in PowerLab Decay, to get better with software and to work together with the company Spire. And we have Mohan Swim from Spire here also. Because we saw that with the integration, there's a lot more potential to get more out of the facilities than small experiments. We can make larger experiments. We say system experiments. So that's a lot about control systems. And our partner Spire has a pretty nice commercial control system, and they would like to deploy it in our labs in PowerLab. So that was part of the motivation. Another part of the motivation is that also we want to activate our labs more. We see that there's a lot more demand for integrating simulations with lab operations. And I think Henrik has emphasized the other important topics already. So we applied for a small project. We got the money. And we've worked with a few people now for a bit more than a year, together with Spire, and mostly the ESAM group of the Center for Electric Power and Energy. At DTU, we do the smart grid research and have some development competence. We have the PowerLab Decay consortium with lots of labs. Here in Riese, we have SysLab, but also the Intelligent Control Lab and the Electric Lab in Lyngby combined our possible facility. Then we have Spire as a partner who has already experience with a lab and in university collaboration in the US, has experience in Denmark to have demonstrated their first level of the smart grid software before. They would like to demonstrate the software further. So going together. The vision for this project is that we would like to have software to facilitate and support the activities in developing smart grids, smart grid labs. So support, you could say, is to simplify and to accelerate, and to facilitate means to enable and connect further things. The other word is the activities. What are lab-related activities? That's a very broad spectrum. We try to boil it down into these 6 categories that you see here. And it goes through different elements where software can play a role. You can have software simulating the physical world. You use software as SCADA system for simulation, and you use it for control systems. And you also have supervision. And then you have further activities, of course, simulating on your desktop. And why would we focus in detail on software? The first part is that software issues are not the stuff you would have in your face all the time, except when you're trying to do things. Then it might get in your way, or it might help you along the way. So it's a means to other ends. But in this project, it's actually our end to make it better. And in trying to define this end, we find out that we see that there are some of our participants in the project are really developers, and others are rather users, and also in our labs. So we want to make this lab software work for everyone. The other aspect has been emphasized, that smart grid control experiments, system testing is becoming more important, and that means the complexity of experiments gets larger. So when the experiment complexity in relation to software gets larger, then software can be a barrier, or if it's good software, an enabler, an accelerator. You can see barrier explains itself. Enabler, I'm thinking of access to data, or being able to connect to devices across labs, being able to connect your control algorithm to devices, etc. And as accelerator, you could say, well, good software allows you to focus on the results. So how do we try to approach this? Because this is a huge domain, and it's not an obvious way to answer the question. Going from a statement that's been referred to in this project a few times, is a good software makes common tasks easy and uncommon tasks possible. If we break this down, then it's about tasks, really. And a lot of the work we've been doing is find out what are these tasks. This big disk here explains the RTLabOS project structure. So we have the part here where we develop ideas for the future together with international partners and with surveys. Also, we have an internal survey where we asked what do people need. And then we have in the blue part use cases. And we've also asked what's feasible in practice and spend most of the time actually on trying to implement some of these ideas. So, and that is also then the outline for this presentation. So first I will introduce the use cases where we try to structure the ideas. And mostly I will present the concepts that we use in context of the use cases. Then we will look at the feasibility studies. We will give an overview first, and then we will have direct presentations from the people who are performing the most part into what they found out and what they've tried. After these three presentations, in the second part, we will look at the surveys. So we will have a survey about the lab users, so Power Lab TK users, a survey we carried out at the end of last year. And then we have made a survey that's a smaller survey with respect to other smart grid labs, some of which may be online listening to us right now. In the end, I would like to summarize what we had learned from some international workshops and then look ahead what should be future discussion. But when we're coming to the looking in ahead, it's really time to also open the discussion. Before we discuss all the items that I'm presenting here, I would just emphasize that in the end, it's good discussion time, but you're, of course, welcome to interrupt me if you have questions about something that's unclear. Let's dig in. So the first deliverable, we have the draft printed here, is called Use Cases for Laboratory Software Infrastructure. And you could say it takes a quarter of the project. What is this about? The scope is defined as that we focus on experiments with a system character because they're more complex than device-oriented experiments, which are already supported. And we want to support experiments that have this closed-loop character, because that's when the experimentation becomes interesting. You send out signals and you have to process them, and then you want to see if it works in a closed loop, the cyber-physical experiment. So that means you would have often several control devices, you will have grid interactions, you will have control and communication software, you will have closed loop of measurements, processing, communication, and actuation. What do we want with this? We want, on the one hand, to identify what are the tasks, these common and less common tasks, and then being more specific, what do they mean? So we do a requirements analysis. This should then, by making it more specific, provide orientation, so we can provide a top-down oriented view and connect it to who are the users, which are the roles. Basically, clarification of what could be in the future. And that should help us then also in the future, and that's also the important point of the discussion, help us organize future development with respect to something that people are developing anyway, so they find a way of talking about it, you could say. The methodology we use is derived of it's use cases. There's a template that's also used in the smart grid era. So there's a public available specification, a template, and we simplified it slightly to meet our needs. But the methodology is now very common in the industry, and it's actually quite good if you get some experience with use cases anyway. So how do we structure it? We use two levels of specification. So sort of high level, what we call the lab business process. There we tell the story about what's happening in the lab, what we're trying to do. And the other level is software use cases, trying to dig a little more deep, take the point of departure in the specific function you want to implement and describe the steps, the interactions of the software that are necessary. In that, we've identified some roles, common actors, software systems, and entities, and we've defined them and made a list, so it's rather structured around these actors. And then we have organized the use case hierarchically into different themes and clusters. So you can see there's an activity cluster 1 and activity cluster 2, that's the theme. And then the lab business processes are associated with the software use cases. Not necessarily as a one-to-one mapping, but when you look at the numbering, it will be pretty much a one-to-one mapping from the motivation. Let's look into this organization at first, because there we have some overview. The first theme of organization is that a lot of the activities are structured around controller development. When you're at the concept design stage, you really focused on the control systems idea. You probably just work with MATLAB or some other simulation tool, or you work with the math. You're not concerned about implementation worries, implementation aspects. So there, the lab doesn't really have a role, but you can still write papers of it. But then you have to start thinking about control software. How am I going to translate this into something that I can embed into a computer, embed into a distributed process? So then we identify, let's say, these different stages. So development, further developing the software into a program, which you might not have deployed on the lab yet, but you're sure at least it's debugged and it runs at the end of this stage. Then you have the period of lab testing, where at the end you can say, okay, this is lab tested, this thing runs, but it's only been seen sort of in the lab context, so you have written the paper about it, but you're not really sure you can show it to sort of a wider audience. That's the last phase, the demonstration, where you want to show that this works. You're pretty confident and should be rather quick to set it up. But there are other aspects. There's another level of maturity here. And finally, field deployment. You see the dotted lines are not really in scope, but these are the main scopes. On the other aspect, there's managing the lab information, lab software, which basically is on the perspective of what does the lab need as software functions. Here we have nice graphics. I'm going to open it again. Here we find some other perspective to look at, you could say, the same problem. Let's look at the first one just to give you an overview. So some of these use cases, they go across several periods. Some only the two, or the last part, some rather the first. So we cover this domain in different ways, but the sequences and the steps, they follow typically this development steps. I would like to add here, so there's one principle. We use the word experiment in different ways here. Inside the use cases, we call everything an experiment that you do in the lab or on the computer, where you have a plan, you want to run it out, and afterwards you know if it's worked or not. If you do an experiment in the development phase, you know your software has passed the maturity level. If you do it lab testing, you know it's lab proper and demonstration. But it's a sequence, a logical temporal sequence of steps. That's the logic here behind these. Then when you focus on managing the lab, we started discussing what would be nice to have. And And one of the features that would be nice to have in functionality is stuff like lab configuration and setup. If you had that as a tool built into the platform and you can just press play and the lab will be configuring itself, that would be nice. Man can dream. But that's what we do. We just say, okay, well, that's a function here. And try to see logically what kind of functions do we need inside a SCADA system. And so some of the functions we have in SysLab, some of the functions you find in other SCADA systems. And there's not necessarily 100% match what the SCADA systems are offering. So these are idealized functions. Data logging and historians are implemented in different ways. Lab configuration I mentioned. A specific thing that's very interesting for smart grid labs and something we offer in SysLab already, that's the control interfaces. Control interfaces means nowadays you can, with SysLab it's easy. You connect to a SysLab node, you know to speak SysLab RMI, and you have an interface to send signals. You don't actually have to worry about what language does this device speak. Is it some low-level protocol or is it something high-level? You don't have to implement several interfaces. That's something that's very practical for smart grid labs, and that's been developed out of practical ideas, also of the idea of distributed control. And we think that has actually is a strong feature we already have that can be built upon. And if other labs would like to copy the idea, they're welcome in that sense. So we've further worked with this idea. And now, because it's so easy to draw pictures, we can also illustrate the idea in a simulation setup. Because in some way, you could think of this, a simulation experiment, to be the same thing. So if you do a similar experiment in simulation, you also need to collect the data afterwards. And if you like the idea of connecting your control software to the lab, why not like the idea of collect your control software to a simulation instead of developing it inside the simulation program? So you can develop your Java-based or C-based controller and then connect it to a co-simulation that is running in Power Factory or some other program, so that you can then keep your software. There's not a complete analogy also. I mean, we don't have model libraries in the real lab. We actually have real devices. But the analogy is strong. So we've discussed it a lot, and it ends up being that actually it helped. We found these devices by thinking of, okay, what would be analogical here? Okay, please bear with me here, because I'm going to do more of these pictures. Because when you could ask again, like, why do you build these dream castles? And I've given different kinds of motivation, that it organizes thought and maybe it organizes the development in the future. But it does something else that may not be so apparent in the first place. On the one hand, when there is already some development, you find colleagues to talk to about the same thing, so we can use the same words. That's mentioned. And the other aspect I try to illustrate with this graphic is, in some way, about the knowledge sharing. It could also help us actually build a meta model of the information we have in the lab and actually structure our wikis, maybe otherwise develop meta information. So we can build tags, etc. And that will help you finding stuff again, if we continue with this. Good. So how does this, I wouldn't say practice, but let's consider now one of these development streams. Then that will be then also the motivation for discussing the following feasibility studies. If you have a control software, you could start developing this against a co-simulation setup. So maybe there's, even in a course, we have a simulation setup, we have a virtual syslab, and we let students develop, or researchers, against this tool. So we don't have to use the lab, the real lab, for the early stages of the development. In the next step, you could take the same control software now, because we've said, okay, could be the same code, move it to the level of the lab. Of course, then you need to do some updates. You will improve your software along the way, but you don't actually have to start from scratch, which you would have to do if you want to implement a controller developed in Power Factory. And if we're bold, we could also say, well, if there's a controller maybe developed somewhere else from another lab, maybe we just make a tunnel and they can control from outside the devices here. Now that looks like dreaming, but it's not. Just as a last part of the use cases, so I've only talked about the storylining. We have developed these ideas a little further in text by going down to the second level and look at the software level. So we have discussed co-simulation development and support infrastructure, which includes describing what an orchestrator does and what this portable agent-based controller could do. Then if you think of control software deployment and energy communication interfaces, we're specifying more about what does this control interface mean in different ways. And also the cross-site integration that I just illustrated. Then configuration management. We have some rather detailed description of what that's supposed to do. And if Oliver were here, you would hear more about that today. But you'd have to ask them another time. Then lab information and management. That's the meta models. That is something we would get back to when we're describing the surveys. So, enough dreaming. So, if we confront people with these ideas, then there would be different responses. Responses that more or less in this sense we've heard along the way. When you are a software researcher, we are some of us here, you shouldn't keep theorizing for too long. You need to actually try out, does it make sense? Does it make sense with software? And also it would be nice to publish something and then we need to implement it. The practical question, I mean, theory is nice, but does it work? Manager perspective. Also interesting for this high level is, okay, how much does it cost? How much work is it? And can we save something if we improve it? How much can we improve? And that's why we needed to get also our hands dirty, and I mentioned it, to do some feasibility studies. So instead of doing all this formal description, we go all the way back and go back to the ideas that were there initially. We wanted to test the system capability of the Lyngby labs with Spire. So that's the first feasibility study we defined. Then from the question of this agent control, can we design an agent control software separated from the simulation platform? That was then feasibility study 2 and 3. Of which you heard about. Then what is the effort from MATLAB-based distributed control algorithms to coming to a lab-operable distributed control software? So this step from the concept to going into the lab. How hard or easy is it to deploy a control software that's been designed somewhere else for a different lab, just on this lab? We'll hear about that. What is the effort and value to implement and offer standards-based interfaces, and which standards are useful? We've tried a few different. What steps are involved in demonstrating an external side aggregator? Also hear about this, we will hear. So basically, all of these things have been performed, most of it within this project. And then we counted how much work it was. We wrote down what are the individual steps and how long it takes. So if there were administrative delays, etc. So this should give us help understand these questions a bit. So if you want to do one of those things or something similar, you can go to the feasibility studies, look who've written it, and get a better starting point. And on the other hand, also we can give a bit of information to the managers to say, okay, how long does it take? So here's a quick, short outline of the presentations we will see now. We will hear from Anna first about these 4 feasibility studies. Then we will hear from Holger who will be online. And then we will hear from Anna. So going ahead, I think, Anna, are you ready?